One of the more interesting lectures, I would say, over the whole quarter, because eyes are super important. Eyes, one of the main reasons, if you take away anything from today, one of the main reasons why a lot of chiropractic neurologists look at eyes is because the eyes and the way the eyes move are coupled with the spine and how the spine moves. And if you're going to look at, let's say, how many muscles are all in the paraspinal muscles total, how many muscles are there? A lot or a little bit? How many eye muscles are there?
6.
Yeah, on each side, 6. So if you know that they're coupled, is it easier to look at 6 muscles on each side or a lot of muscles in the spine? You can learn a lot about the nervous system and how we do balance and posture and all that stuff through the eyes a lot quicker than you can through motion palpating or static palpating all the way up and down the spine. You can do that, and it's great to do that, and I encourage you to double check yourself and do a lot of that stuff. But if you've got, a limited amount of time, you can do something with the eyes. You can look at a pursuit or a saccade. If you don't know what that is yet, we'll explain it to you. And you can get a huge window into their nervous system based on what it's showing you, what that patient's showing you. So a little bit last time we talked about the two main differences there's multiple eye movements, but the two main ones that we're going to be talking about are saccades and pursuits. So what's a pursuit? Tracking, okay. So what's a saccade?
Jumping from one target to the next.
Perfect. So jumping from one target to the next. What's up, guys? So if I was going to pursue a moving object, a moving dot, or whatever, to the left, what part of my cortex would be involved in following something to the left?
Right.
So if it's a pursuit, it's parietal. Think P and P. So PP. It just goes together. It's the same thing. So it's the same side. So ipsilateral or the same side parietal lobe. So there you go. There's a window into how that parietal lobe's doing, right? If you can't do it, maybe something's going on with that, and you need to dig a little bit further into it. So if I pursue something to the right, what part of the cortex is it? Right, parietal. Okay, now let's switch it up. So if we do a saccade, like we said, it goes from one thing to the other thing, like from there to there. There's no following in between, just A to B as fast as you can. Okay, what part of your cortex is that? Frontal. Is it same side frontal or opposite side frontal? Opposite. Good job. So if I saccade or if I jump to the left, it's a right side frontal, which is kind of easy to remember because the frontal lobe controls the opposite side part of the body, right? So if you know it's frontal, it whips it to the opposite side. Okay? So we talked about, so we didn't talk about homologous column. Homologous column is if those cells and those neurons are born at the same time, they function at the same time. So, for example, if I look to the left, I have one completely different nerve over here, and one completely different nerve over here, and one completely different muscle over here, and one completely different muscle over here, working at the same time to get over there, right? So I've got an abducens nerve to a lateral rectus muscle shooting my eyes left, right? Okay, what muscle is over here, let's do it this way. What nerve, and this is in the manual so you guys can kind of cheat, what nerve shoots to the medial rectus to shoot your eyes left? Oculomotor. Okay, so you guys got to learn trochlear nerve, which is cranial nerve number, what's number 3? Okay, and what's 6? Abducens. Okay, so if you guys don't know those, if you guys don't know the nerves that control eye muscles themselves, that's something that we don't really have time for in this club, so I'm going to make it as basic and as clinical as I can, so you guys can go and turn around and learn that stuff on your own deal, because that stuff's boring to teach, and we don't want to do that stuff in here. Fair enough?
There's some really good stuff on the research part of the website. There's one chapter in the book that's from Fundamentals of Neuroscience, and it's all about eye muscles, eye movements, and makes it pretty basic, breaks it down by cranial nerve, so definitely go check that out.
Cool. And Bryce has been killing it on that research part of that website, by the way. So if you guys want to go to the website, it's just parkerneurologyclub.com. Go to
Learning or something. Classroom, then going down to the research articles and stuff, and like for every club, he throws down like a ton of different stuff. You don't need to sit there and read like the stats and all that stuff. Just unless you really want to and you're into that stuff, just read the abstract and you're good. And that can tell you a lot about what they did, what they found, and then like move on to the next one. That'll tell you a lot. So we talked about great window. We're going to talk about posture, balance, and biomechanics in a second. How many of you guys have, when we were doing all these tests so far in this try, have done something like the balance test and you got them to close their eyes and that's when their lesion came out? So a lot of us are like that. A lot of us, we use normally around 60-70% proprioception at a time, then we use vision and vestibular system a little bit less, and that basically, when you add all these things up, you figure out where you are in space, and that controls your posture. Why do chiropractors care about posture and balance? It's kind of what we do, right? We're always looking at x-rays, we're looking at different stuff to affect posture and all that stuff. So eyes can be huge, huge, huge compensatory factors. So if you're looking at somebody's posture, it may not be their proprioception. It may not be something that you adjust to make better. It might be their eyes that are messed up. And we'll teach you how to rehab those today. So if you fix your eyes and you adjust them, it'll hold, right? So that's huge. Can benefit adjustment. So we talk about stuff like that. So in cerebellum, which way, if I wanted to make my cerebellum stronger on the left, which way would I look? Left and up. So can I borrow somebody to go face down right here for me real quick? So let's say we cleared Tyler. Tyler's good. He's got good eyes. Let's go face up. His eyes are good. The vestibular system's good. And we wanted to adjust him. And let's say he's an athlete and we know that he's got really good metabolism. He's got all these things that he can take a really strong adjustment. So we want to do something in his neck. We adjusted his neck and it kind of came back. We want something a little bit stronger, right? So we know that if we want to, and if I adjust him on the left, so he's a little bit more, I would say need to be adjusted on the left. So if I was going to adjust him on the left, and I wanted to make that adjustment stronger, first of all, we know that if I adjust him on the left, it's going to go to that left cerebellum. But maybe I want to activate that left cerebellum a little bit more, so I'm going to get him to look up and to the left, right? Which is pretty easy because I'm going to send him that way anyways. So if he goes up and to the left, I just say, hey, look at me. You know what I mean? So if I was going to do it, I would set him up right here. And I would say, hey, Tyler. And then he's already up and to the left, right? And then you can hit him right there. And that's a really easy way to boost your adjustment because a lot of times things stop. I don't want to do it because I want to get in trouble. If you guys want to practice that, go for it. But, yeah. I don't care. But we talk a lot about how to kind of dull your adjustments down, maybe if they're too strong. Or a lot of times if it's an athlete or if it's somebody that comes in, they work out all the time, they're really in shape, and they want a good strong adjustment, there you go. Another thing that you can do is, we're talking about homologous columns, is when you look up, it's a coupled movement with your inhalation. So we don't think about that a whole lot because we don't think about every time we breathe we don't look up. That doesn't count. It's just when you do look up, it helps the ventral horn cells fire to the muscles that make you breathe in. So anytime you do a rib adjustment, if you have them lean back on you, you say, all right, breathe all the way out, and then you breathe all the way out, because if you have air in your lungs, when you're trying to do this, it comes out of your lungs. Does that make sense? So you kind of breathe out too, you let them breathe out, you say, okay, breathe in, look up. And as soon as they look up, you hit it, and it goes a lot easier that way. So there's two quick ways that can help you out in your adjusting. Just by getting them to look certain different directions, you're getting them to fire into their nervous system a lot stronger than it would be normally, right?
Hey, Jake.
Okay.
Will you explain like stronger adjustment real quick versus like?
Yeah. So let's say you want to reach a certain frequency of firing in the cortex with whatever you're doing, or frequency of firing anywhere in the brainstem, whatever. And we know that. Let's actually draw that out. Okay.
You got a marker?
All right, so this is where, let's say this is negative 70, and this is where your nerve kind of sits normally. It's charged. It's sitting at negative 70, like milliamps or whatever it is, right? And we know that for it to fire onto that next nerve and create a synapse and fire and to create communication in the nervous system, it would need about 70 milliamps to jump up to actually fire and depolarize back down to do it again. Does that make sense? Has everybody had some sort of physiology to know how a neuron fires, right? Let's say we adjust them the first time and we don't get the activation that we want. We say once he fires these nerves in an adjustment, as soon as it actually fires, it can maintain a better level of health in the systems that we're trying to fire in the central nervous system. So we didn't get that. We got it like right here. The adjustment we gave him was probably like 50 milliamps based on the activation that we gave him. It wasn't enough to synapse the rest of those neuron pools in the cortex, and it went right back down to a resting rate. Right? So now we just want to boost it with something else. Am I making sense? So we want the pools, let's say it's in the opposite cortex or in the brainstem, we want them to fire better because we want it to hold. We want them to reach that state. We're maybe not in that rehabilitation window that, we can maybe push them a little bit more with the stimulation. So that's when we would do something like that. You get it all the way up to fire, and then it would keep going.
So, to kind of like think about it, in the first place, the needing adjustment wouldn't even be like hyperpolarized
Yeah.
instead of at 70?
Yeah. So it would be even lower than that. Good call. So you would want, but if you think about that, you also have to think about the other side where some people maybe can't handle a super, super strong adjustment, but just because they're hyperpolarized. So yeah, -70 is where it sits normal. So.
You may have already answered it. So what are the short and long-term consequences of then overdoing it?
So that would be, let's say we crash them. Let's say we burn all the glucose, all the oxygen. The nerve kind of goes into, and not just that nerve, but that nerve pathway kind of goes into a state of survival rather than functioning to the next neuron that it communicates to because you've blown all its energy.
Gotcha.
So once it's worn out, it's going to worry about itself first. It's like, I need to stay alive. I don't really care if I have to talk to other people right now. I'm just going to focus on me. And you don't get communication in those pathways.
Awesome.
So, and we can talk about that a lot too. We can talk about different ways you can boost something, or, it just doesn't have to be vision. It can be, you can spin them first. You can do a bunch of different stuff. I think that kind of confuses people though. So we're going to stick to vision for today and eye movements and stuff like that. Another thing that a lot of people don't really have is gaze or gaze fixation. So a lot of times, Tyler, can I get you to come back up here for a second? Would you play baseball? Okay. So let's say a Major League Baseball player comes in and he's like, I got hit. I had a collision with one of my players during the outfield, went for it, and ever since then, I've kind of had blurred vision a little bit. My reflexes are a little bit slower. I've been going to a chiropractor. It's helping a little bit, but it's not really helping my coordination with my eyes, my eye-hand movement, stuff like that. So we want to look at his gaze fixation. So a lot of times what we can do is we can look at his eyes. So let's go ahead and just do like a swing stance, like a pre-swing stance. Okay. So we can have him right there. We can have him look at a dot right here. And then we can go ahead and track his eyes right here. And then we're going to get him to stare at a dot. Now go through your swing stance, all the way to swing phase, and hold right there. So at that one point right there, his eyes went doo-doo.
Yeah.
So we're going to get him to hold that part right there because that's where his body lost where he was in space, which caused him to lose it, right?
Wow.
And if a pitch is coming in at 90 miles an hour, he can't afford to did it. You know what I mean? Or if it's coming in, he's running. Because think about him, if he can't even do this and have his muscles in his eyes be coordinated and smooth and doing exactly what he wants. If he's like running in the outfield trying to dive after a ball, or if he's turning a double play, like whatever, it's not going to happen as well as it could. Make sense? So we're going to get him to go right in that swing phase, right where he messes up, and we're going to do the rehab right there until it's better. And then when it's better, he can finish the swing, and then we do stuff like that. So it works the same thing in golf. It works the same in soccer. If you can hold and do it like that, and you see people doing all this. If people can't balance here, they're not going to have good movement. They're just not. They have no idea where they are in space. So thanks, Todd.
That's incredible.
So that's something you can do too, is you're rehabbing them. So in the same thing, so you go in, their eyes are good, but they're still dropping their scapula. They're still losing something. That's when you can go in and adjust them in that movement. Does that make sense? And a lot of chiropractors don't do that. They'll take an athlete and not use their athletic specific stance at all. They'll just say, yeah, lay down, hit them a bunch of times, and it doesn't help them as much as it could because it's not in their specific movement. So use whatever technique y'all want. Figure out how you can do it to make it as specific as possible because the nervous system is super specific. We learn super specific. So So we were talking about saccades and pursuits and stuff, and we were saying that it's a good window if it's a pursuit, you're looking at the parietal lobe, and if it's a saccade, it's a frontal lobe. But we can also look at it in terms of the actual eye movements themselves as a good indicator and a good window of the midbrain and the pons. So where is cranial nerve 3? In the pons, in the medulla, in the midbrain? Midbrain. Where's 4? What's 4 again? Trochlear. Where's the trochlear? Or the nucleus. That's also in the midbrain. So 3 or 4 are midbrain. 6 is in pons. Is the midbrain more sympathetic or parasympathetic? Sympathetic or parasympathetic? Midbrain sympathetic. So if we're looking at, let's say, cranial nerve 3 and the abducens nerve, sorry, not the abducens nerve, the trochlear nerve, and those are the eye movements, so the trochlear nerve goes to what muscle in the eye? Superior oblique. What nerve what muscles do the oculomotor nerve go to? All of them except the superior oblique and the lateral rectus, right? So you can just say follow my thumb, and depending on which way you look, you just figure out, you just match them up. And that's not something we have time to go over to today, but just look and see what your thought process should be. What direction did their eyes go? What muscles had to get them over there, and what nerves had to get them over there? What nerves are controlling the muscles, and then where do those nerves come from? Because that's all the doctors do, is the doctors look at those nerves and say, okay, those nerves are all in the mesencephalon, so the mesencephalon sucks. So we're going to rehab the mesencephalon. It doesn't matter if you rehab the eye muscle, because the eye muscle is doing exactly what the crappy mesencephalon is telling it to do. Okay?
I have a question, Jason.
Yeah.
I thought about this before. It's kind of hard sometimes because, like, let's say you're doing a pursuit to the right and you see a little bit of saccade or nystagmus or something. You have to look at both eyes. So sometimes you have to. How can you determine which eye or which muscle? Because you're using a lateral rectus on one eye and a medial rectus on the other.
So let's say it's like and we'll talk about this in a second. We'll talk about skew deviations, to where the eyes kind of do this. A lot of times what they'll do is they'll cover up one eye and they'll track. The other thing you can do is don't look at one eye individually. You can look right in the middle, and then you can kind of get a gauge of if they're both doing it or if only one's doing it or whatever. A lot of times what we do is eyes are kind of easy to do physical therapy on, because especially if it's like pursuit or something and they kind of break out and it's not even when they pursuit, you go back right to where they messed up and you just kind of give them a little something to follow right there, and it can normally even itself out. And it's normally not as, it can be as simple as that, so try that. But that's a good question, because a lot of times you'd have to break them up. I think we'll actually come back to that later today too. So let's talk about how it affects biomechanics. So as chiropractors, no matter what your technique is, this is going to happen a lot, and you'll see this a lot. So what do you guys see? Do you guys see anything wrong with this guy?
Head's tilted.
Head tilt. What about his eyes? It's droopy on one side. So speaking of a skew deviation, this is what a skew deviation looks like. So when we talk about how do eyes affect the biomechanics of the spine for chiropractors, this is one of the examples of what happens. So for this one, we're going to talk about the superior oblique. So here's what happens. So let's say, where's the superior oblique again? What nerve is that? Trochlear nerve. And where is the trochlear nerve at? Mesencephalon. So let's say somebody's really, really sympathetically driven. They're super wound up and their mesencephalon crashes because it's always firing, right? So what happens to that superior oblique? It goes through that trochlea, that little bony pulley, which is why it's the trochlear nerve, because it goes through the trochlea, right? And it comes and loops back. So if it's this eye, that muscle comes forward, loops around the trochlea, and it attaches back towards this eye. And its job is to basically pull my eye down, right? And it's got a little bit of torsion on it, but its job is to basically pull it down, okay? So if I've got the inferior oblique, which job is to pull up, and that superior oblique is job to pull down, and the muscle that's job is to pull it down is weak, you're going to see the eye go up. Everybody follow that? If I've got a muscle, and it's basically tug of war in my eye to keep my eye straight, I've got one muscle's job is to pull the eye down, the other muscle's job is to pull the eye up, and the muscle that's job is to pull it down is weak, it's going to go up. If my biceps job is elbow flexion, and my triceps job is extension, and my triceps are weak, you're probably going to have more flexion tone. Same thing. So what happens is the mesencephalon goes to crap. That trochlear nerve doesn't fire the way it should, so that superior oblique doesn't fire the way it should, and the eye rolls up, and you get a little bit of torsion. So when you see that, it goes up, goes into torsion, you're going to get a head tilt because you want to compensate for the eye that just rolled. As soon as you get a head tilt, you get that little, now that skew deviation is talking about the eye. So now one eye is going to look higher than the other because it just rolled down and over, and you're going to compensate, right? But now you get a head tilt. So you can go in there all day long and adjust that head tilt, and it's going to keep coming right back, right? So, and you see it. So if you guys study for a long time, if you guys have study parties and you guys just are wore out, or if you guys get really drunk or whatever, you're going to see your friends start to have a skew deviation. And you'll just look at them and be like, boom. So that's something that you can go in and you can do. So we're talking about mesencephalic eye movements. We want to strengthen that eye that's kind of weak. And by strengthening that eye, it'll fire that trochlear nerve, and it can help the mesencephalon kind of even itself out, right? So we want to go in and we want to do, whether it's saccades or pursuits and general directions, we want to kind of fix that out. We might have time to get in that today or not. I'm trying to keep this kind of basic. But is everybody following that so far?
Your head tilts toward the side of the lesion.
Normally, yeah. So you're normally going to go, if it's the right side, right mesencephalon, you're going to go right head tilt. So, and Spencer, do you want to add anything? So far, so good?
I got something to say. I can say it right now.
Okay.
One of the studies that I posted on there is really cool. It's a 2014 study, so pretty brand new. And they looked at people who had just had mild traumatic brain injuries and their eye movements using saccades. And basically, I'm not going to sit here and explain the whole study, but they found a correlation in decreased function with people mild traumatic brain injury, obviously. And the conclusion that they made was that using saccadic rhythm and observing eye function is looking like it can now be an early detection method to tell if people are recovering from their traumatic brain injuries or if they're going to go through chronic symptoms. It's like one of the earliest detection methods that we know of right now, even more so than doing a MRI on them. So this stuff is pretty cool. I mean, that's a recent study, but getting this stuff down really can tell you a lot about the brain, what's going on in the brain.
And that reminds me of, so going back to saccades. Saccades, we're going to talk about those for a second because that's got three main things you can look at. So the saccade is when you go from this point to this point. So you can do that by either flicking a thumb, by watching a screen where it can actually move and doing whatever, but the point is you've got to go from this point to this point. So you can check for a couple different things. You can look for something called latency, which is you're comparing the time of the stimulus to the time of the actual eye movements. How long does it take your brain to figure out, hey, we should go and look over there? Saccades go up to 700 degrees per second if they're fast. They're super fast, and that's a very, very smart person. You can't be kind of like, I don't want to say kind of dumb, but like, let me flip it. You have a very, very good brain if you've got fast saccades. Like you are moving on all cylinders, you are firing very, very well. Those are like your geniuses, right? People that have very high functioning brains, you can look at really fast saccades and they're going to be all over the place and it'll stick. Good brain, right? So latency, how long it takes your brain to figure out, hey, there's a new target and to jump to it. Okay? There's also the velocity. So after your brain has figured out, hey, now that we know there's a new target, how fast does it take you once you start moving to stop moving over here? Okay? So that's also a good indication of brain function. How fast that saccade is to flip over there and get there and stick. And then you've also got, once you actually stick right here, your position. So if you've got a position where you are in space, let's say if you overshoot it. So let's say I'm going this way, and I land right there first, and I have to jump back. It was probably actually firing too high because it overstepped where it should be, and it's got to jump back. So, how much time do we have? Do we want to get into that? Would you guys rather adjust today or do blind spot mapping today? And showing how adjustment affects the brain.
Blind spot.
Blind spot? Cool. All right. So we were comparing frontal lobe. So the frontal lobe throws it over. Let's say I'm looking over here at a left saccade. My right frontal lobe saccade's over. The cerebellum kind of catches it. If the frontal lobe is too high, it's firing too high, it'll overthrow that saccade and it'll go past the target and it'll come back, hypermetric. If it's not working enough, you'll see it underthrown and it kind of does like a two-step because it didn't get thrown over enough. So if it has, let's say you're looking at the eyes, you're looking at somebody's nose, and you say, look right here, and it goes bing, bing, right? It's under, it's a hypometric saccade. What frontal lobe isn't working? What side would you adjust them on to see if you can speed it up? Right body to the left frontal lobe, right? Because technically it would go left parietal, left frontal. Okay? So let's say you're doing a pursuit, and you're saying just follow my thumb, and you follow it, and it's great to the right, great to the right, great to the right, great to the right, and then you come back to the left. Well, I guess the patient's left would be that way, and it's bad. There you go. You got a bad. Well, assuming they were on the same side, because that would really look like a real patient if you had a bad frontal and a bad parietal on the same side. Then you'd really want to adjust them on the opposite side. It's like, man, your entire cortex isn't doing so hot, right? And it's really easy. You kind of like eyes because they go through all the different parts of the cortex. If you look at something, it's not just your occipital lobe, and that's what a lot of people think, because yeah, you process it in the occipital lobe, but if you close your eyes, it's got to go through temporal because you got to remember where it is that you saw it, right? Like whoever's been in a room where they set something down, they turn the lights off, and they have to go back and get it in the dark, and they're like, I think it was like right here, right? So your occipital lobe has to communicate with that temporal lobe. And then it has to communicate with the frontal to figure out what you're going to do about it. So if you're going after a ball, like a moving target or a football, you have to be able to move where you see it. So you have to use a lot of this vision, and the vision just lights up the entire cortex because of those different things, because it has to communicate with a lot. With that said, if the vision's bad or the movements are bad, your cortex gets really messed up and you don't know where you are in space, and then you get subluxations because your brain's trying to compensate for where you think you are in space. So let's do the blind spot. So this is what the blind spot is. Let's do, I wish I had a different place to write. We could use that.
A lot of these things are really hard to observe by watching someone. I mean, like latency and some of those things. But on some of these studies that they have, it's crazy. And they actually call it saccadometer or saccadometer. I don't know how you pronounce it. Saccadometer, yeah. And it's crazy how they can literally take all this data, just watching your eyes, doing all these different tasks.
Are there machines that...
Yeah, pretty much like glasses that are stuck on your head that have cameras and they're watching your pupils.
It's like a laser.
Yeah.
And you put on this thing, and it's like you're going like mining, like those little like helmets with the flashlights, and it'll just project out a laser on the wall. And every time it moves, it'll measure how fast your eyes go. So it'll measure that velocity. It'll measure that position where it sticks, if it has to change or whatever. It'll measure the latency, how fast it goes, and then you print it out. And then it'll go, okay, you're slow over here, and pretty much it'll give you an idea of like, I want to check to adjust here, 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 and then I want to redo it. Because I just sped all that stuff up. So in 1994, this is what we're about to do. In 1994, Dr. Carrick came out with this study, and he was like, right now, nobody's really doing research on, everybody's doing research on adjusting and that communication between the brain and that peripheral, not receptor, but the peripheral organ. So that end organ, either the muscle or your autonomics or whatever. And like the research wasn't coming out great. They're like, sometimes it worked, sometimes it didn't. And so he came out and he was like, we're doing this the wrong way. We need to do research on the adjustments effect from the peripheral nerve up to the brain. And how can we figure out that we're making a change by adjusting? So what he did is he did a blind spot map where you start with a dot in the middle, and you stare at the dot, and then we're all about to do this in a second. to where you stare at a dot, and then as you stare at a dot, somebody moves, like let's say this was all white with a black tip. You start to move it away, and all of a sudden that black spot disappears. It goes into your blind spot. And then you keep moving it, and then it comes back. And then you start to go up, and then it comes back, and then you start to go down, it comes back. So basically you have this hole where your retina is, where you have a blind spot. And your brain, and the healthier it is, the healthier it can basically fill in that blind spot for you. And if you do it on the other side, it's the same exact thing. So what he found is people's blind spots were different on each side. So he would go in, and he would adjust them, and then they'd basically recheck it and figure out that the blind spots would be normal after he adjusted them. So the brain would be firing better, it would fill in a better blind spot, and then you'd be like, wow, this is great, right? So that's what we're gonna do. So everybody pull out a sheet of paper. Who's above, who's tried